Hello everyone, and welcome to our video on partial fractions. So in this section, we're going to be looking at integrals that involve proper rational functions. That means a polynomial divided by another polynomial. And the first type of situation that can arise is when the power of your numerator is equal to or larger than the power of your denominator. So if we look at this example here, the integral of x cubed plus x over x minus 1 dx. What we notice is that there's no way to factor this and cancel the term in the denominator, so we can't simplify it, not as is, but also the power of the numerator is a third degree polynomial, and the denominator is just a first degree polynomial. So when this occurs, when the powers of the numerator and denominator are higher or the same, in this case, the power of the numerator is higher, we can use polynomial division to rewrite the expression. Now, many students have primarily learned synthetic division for polynomials, and synthetic division is a great quick process for dividing polynomials, but it's a little bit limited. It only works when you're dividing by linear factors, so for this example, it would work. But we aren't always going to be just dividing by linear factors. And since I find that my students are often more rusty with the idea of polynomial long division, I'm going to do this example using polynomial long division. And I'm going to kind of, off to the side, do a regular division problem, just to illustrate how this is very similar to regular division. So first thing I'm going to do is write out my division. So what do we got? We've got, here's our division bar, got x cubed plus x. And one of the things I'm going to do is put a placeholder for every power of x that's missing. So x squared, I'm putting 0x squared. And for the constant, I'm putting 0 as well. And then I'm dividing this whole thing by x minus 1. Now, I'm doing that in order to keep track of which terms I've actually done my dividing out by properly. Now, you'll see we actually do this when we're dividing regular numbers. We just don't think about it. If I have 1051 and I want to divide this by 3, I don't leave the hundreds place blank just because there's no 100s there, right? I put a 0. So we're doing the exact same thing here. Now, if we look at this division problem, we say, well, 3, I can't feed it into 1, but how can I feed it into 10? In other words, what's the biggest number multiplied by 3 that's still less than 10? And that would be 3. So I multiply 3 times 3, I get 9, and so I'm removing that portion so far. So really what I've done here, look, this is in the 100ths place, so I've removed 300 times 3 of this portion, 1051. And then I drop this 5 down. I've got a 15. I go, okay, what about this? How many times does 3 go into 15? Oh, 5 times. 5 times 3 is 15. Nice, I can just remove that. But again, really what I have left is 151, and what I've done is removed 150 of that. So I've removed 150 of that, and now I drop this one down here. And I can't put 3 into 1 at all. So I get a 0 there, and I have a remainder of 1. And what does this say? What am I really saying here? I'm saying that when I take 1051 and divide it by 3, that's the same thing as 350 plus 1/3. And that's really the key here. This is the part that we care about, because that's what we're doing with these polynomials, is we're rewriting them as a whole polynomial plus a fraction over the divisor here. So, okay, let's get to it. I'm looking for how many times x can go into x cubed. And I think, well, x times x squared is x cubed. So 1x squared, when I multiply that by my x, will give me x cubed. When I multiply it by -1, I get negative x squared. And then I subtract these, just like in regular long division. That gives me 0 minus a negative, so that's plus x squared. And then I got to drop down this x. I go, okay, well, what can I multiply x by to get x squared? Oh, just a single x. And x times x minus 1 gives me x squared minus x. Subtract them. Minus the x squared is 0. And then x minus a negative x becomes plus x, so that's plus 2x. And I pull that 0 down as well. So how many times does x minus 1 go into 2x? Well, I can multiply x by 2. And so when I do 2 times x minus 1, I get 2x minus 2. And I subtract it. So what's left? It's just 2. That's my remainder. So the key part then is that x cubed plus x divided by x minus 1 can be written as the polynomial x squared plus x plus 2 plus the remainder over x minus 1. So now if we go back to our integral, I'll call this I. That means that we can rewrite everything that's inside the integral. So we can just write this as I equals the integral of x squared plus x plus 2 plus 2 times 1 over x minus 1 dx. And then we can integrate like normal. X cubed over 3 plus x squared over 2 plus 2x plus 2 times. And you would normally do a u substitution here, but u is x minus 1, so du is dx. So I'm just going to skip that. It's a pretty simple one. It's a natural log of x minus 1. And then tack on a constant. Okay. So that's it for that one. Again, anytime you've got a polynomial divided by a polynomial, and the power of the numerator is equal to or greater than the denominator, you can try rewriting it using polynomial long division. Now, the rest of our problems here are going to be focused on something that should be a little bit more new to most students, which is partial fraction decomposition. So partial fraction decomposition is a result that comes from linear algebra. And regretfully, since linear algebra is not a prerequisite for this course, I can't really give you a rigorous breakdown of why partial fraction decomposition works, because we don't have the prereq knowledge for the class. Nonetheless, it is a very important process that we've got to be able to do in order to solve a lot of these integral problems, so we're going to go through the process together. All right, now there's several cases, and we're going to break these down one case at a time. So the first case, our function in the integral is, and we're really not talking about integrals right now, we're just talking about rewriting the fractions, but the function that we're concerned with is a proper rational function, meaning the numerator and the denominator are both polynomials, and the degree of the numerator is smaller than the degree of the denominator. And on top of that, for case 1, we look at the denominator being a product of distinct linear factors. So that is, q of x is a linear factor like a constant, a1 times x plus a constant, multiplied by another constant times x plus another constant. So a product of a bunch of linear expressions where none of these factors is repeated. None of these will be the same expression twice. Then the partial fraction theorem from linear algebra guarantees that there exists constants a1, a2 through ak, such that you can rewrite your original fraction as a constant divided by a linear expression plus a constant divided by the next linear expression, so forth and so on, for all of the linear terms in the denominator. So what that means is if I can write my denominator as a product of distinct linear factors, then I should be able to separate those factors out and write something a little bit easier. Basically, this process is really just the reverse of combining fractions, right? We know we combine fractions by finding common denominators. So this process is just the opposite of that. Instead of finding common denominators, we're actually trying to separate out the terms of the denominator. But in order to do that, first, we might have to factor. So I look at this expression, evaluate 1 plus 6x, the integral of 1 plus 6x over 8x squared plus 14x minus 15. And I think, well, let me start by figuring out how to factor that denominator. So I've got 8x squared plus 14x minus 15. And since I've got a leading coefficient other than 1, I'm going to multiply this 8 and this negative 15 together. And that's going to give me negative 120. And so the approach I like to use, I know students learned a lot of different approaches for coefficients other than 1. The approach I like to use is factoring by grouping. But first, we're going to look for factors of negative 120 that add up to 14. That's our middle term. And you could go through a whole bunch of these, but I noticed that 120 is divisible by 20 and 6. And so positive 20 and negative 6, those factors, when I add them, 20 minus 6 is 14. So that's exactly what I want for my factors. And so what I'm going to do is rewrite this as 8x squared plus 20x minus 6x minus 15. So all I've done is rewritten 14x as 20x minus 6x because those are my shared factors for this 120. And then I factor each pair of terms separately. I'm going to factor this and factor this with common factors. I got a common factor of 4 and x, so I get 4x times 2x plus 5. And here the only common factor is negative 3, and I get left with 2x plus 5. So I've got 4x, 2x plus 5, minus 3, 2x plus 5. And so I factor that 2x plus 5 out, and I get left with 4x minus 3 times 2x plus 5. So I can rewrite my integral as the integral of 1 plus 6x over 4x minus 3 times 2x plus 5. Now we're going to do our work on our partial fractions. So when I look at this fraction, 1 plus 6x over 4x minus 3 times 2x plus 5, this is exactly the situation described in case 1 above, which is I've got two linear expressions in the denominator, and so I can rewrite this as a constant over the first linear expression plus a constant over the second linear expression. And now what I have to do is figure out how to solve for that. All the partial fractions theorem tells me is that there are constants that will make this true. Solving for them is up to us to do algebraically. Now, what I'm going to do is find a common denominator here, 2x plus 5. 2x plus 5. And over here, I'm missing the 4x minus 3. And so then I can combine those fractions together on the right side. get a times 2x plus 5 plus b times 4x minus 3 all over this thing. 4x minus 3 times 2x plus 5. Now, I'm usually going to skip this middle step because I know the whole reason I found these common denominators here, right? I multiplied by the missing factor in each term. And I did that because I wanted to cancel these denominators. Now that I've got both sides of the equation with the same denominators, I can cancel them. And so I can go now to saying 1 plus 6x is a times 2x plus 5 plus b times 4x minus 3. So I'm usually going to go straight to, in the future, straight past that middle step. I'm going to go straight to this. Let me just move this over here. Okay, now I want to solve for a and b. And there are a lot of ways you can solve for a and b in this type of problem. I'm going to do what's the simplest way in this case, but we might have to take different approaches later in some of our later examples. So, okay, what I'm going to do here is say, hey, this equation has to be true for any value of x, which means I can plug in values of x and solve that way. Now, I could plug in any value of x and build some systems of equations, but if I'm really clever, I can pick the values of x that will make most of my terms disappear. What do I mean by that? If I can get rid of this a, I'll be able to solve for b really easy. So I ask myself, hey, what does x have to be to equal 0? Well, x would just have to be negative 2/5, right? Just set it equal to 0, solve it, x is negative 2/5. So that's what I'm going to do. I'm going to plug in x is negative 2/5. I get 1 plus 6 times negative 2/5 equals, this whole first term is going to be 0. That's why I picked x as negative 2/5. Plus b times 4 times negative 2/5 minus 3. And now we solve for b. So we get 1 plus 6 times negative 2/5, that's negative 12/5 equals b times, this is negative 8/5 minus 3, so that's negative 8/5 minus 15/5. 1 minus 12/5 is going to be negative 7/5. And over here we're going to have negative 23/5. The 5's will cancel, and I end up with b is 7 over 23. The negatives also cancel. So there's my value for b. And now let's also find our value for a. So how do I find my value for a? Well, in this case, I go, well, can I make this term 0? So I can get rid of the b in the expression? And I can. I can just let x be, well, what would I need? I would need 3/4, right? So 3/4. And so what do we get? We get 1 plus 6 times 3/4 equals a times 2 times 3/4 plus 5 plus 0. So this is 1 plus 18/4 or 9/2 equals a times 2 over 4 is 1/2, so that's 3/2 plus 5. 1 plus 9/2 is 11/2. And 5 is 10/2 plus 3/2 is 13/2. The 2's cancel, divide the 13, we get a equals 11 over 13. So now we've solved for our missing constants, and we can rewrite our function in terms of the a over 4x minus 3 and b over 2x plus 5, right? That was the whole goal here. So I'm going to do that, but I'm going to plug it straight into the integral. So now we can say, all right, the integral is now written as a 11 over 13 over, and it's always a good idea to double check which fraction was where. A was divided by 4x minus 3, so we want to make sure we put it in the right place. 4x minus 3 dx plus the integral of 7 over 23 over, and our other factor was 2x plus 5 dx. Now I'm going to shrink this down just a little bit since I didn't give myself a whole ton of room. But these are relatively simple substitutions. You would do u equals 4x minus 3. So you would get 1 over u. Well, you'd get the constant over u. And you'd end up dividing by that constant multiple of x. So I'm going to skip that u substitution step because, again, something we did a lot in those u substitution problems. But we'll get the natural log of 4x minus 3, the absolute value of 4x minus 3 over 4, plus 7/23 times the natural log of the absolute value of 2x plus 5 over 2 plus c. And finally, I'll just simplify this slightly further. 11 times ln of 4x minus 3 over 13 times 4, and that's going to be 52, plus 7 over 46 times ln of the absolute value of 2x plus 5, plus c. Did not leave myself a lot of extra room. If you ended up a little crowded on your notes, I apologize. Okay, well that's it for that one. Let's move on to case 2. So in case 2, our denominator, q of x, is a product of linear factors, some of which are repeated, right? So in other words, when I factor out my denominator, I might get some linear expressions raised to a power other than 1. Then for each factor, each of them that has a repeated, for each repeated factor, the decomposition will have k terms of the form. K is the number of repeated factors you have. K terms of the form, a constant over the linear factor, plus a constant over the linear factor squared, plus a constant over the linear factor cubed, so forth and so on, up to that number, which was however many times that linear factor repeated. So when I look at this one, first thing I'm going to do, as always, is factor. So I factor out the x squared. I get 5 minus 2x. Now, one of the things that often trips people up is they see this x squared and they think of it as a quadratic factor. But in this context, we're not thinking of this as a quadratic factor. We think of it as a repeated linear factor, because I can write this fraction, instead of x squared, I can think of it as x squared, where x is a linear factor. So this is a linear factor x being repeated, multiplied by itself. So what the partial fractions theorem tells us is that for this x repeated linear factor, x to the second power, we can write a over x plus b over x squared. Now we have another linear factor, 5 minus 2x, so we add another constant over that linear factor. Now we go to our next step, which is to find our common denominators and simplify our expression. Remember, I said I was going to skip that part because we know what's going to happen. I'm going to multiply a by the missing factors. I'm missing one factor of x, and I'm missing 5 minus 2x. Then I'm going to multiply b by my missing factors, but I've already got the x squared in the denominator. So the only factor I'd be missing to find a common denominator is 5 minus 2x plus c, and there I'm just missing an x squared term. And once I found my common denominators for these terms, I'm going to cancel out all the denominators anyways. So I'm just skipping straight to that step. Okay, so now in this case, I have two factors, two terms that have the same linear factor. So when I pick an x value to cancel this term out, it's going to actually cause two of them to cancel out. So we probably are going to have to do a little combination here. We can do some clever choice of x values to solve for constants, but then we're still going to have to do a little bit of more rigorous algebra, let's say. Okay, so we'll start by choosing the easy, most obvious choice for x. How do I make the factor x 0? I just set x equal to 0. And plug that in, and the first term will be 0 plus b times 5 minus 0 plus, and the cx squared will also end up being 0. So we get 10 equals b times 5, and so b is 2. Okay, now how do I get rid of this term? All right, so like I want to get rid of this one, the term with b. So x would have to be 5 halves in this case, right? If you set this equal to 0, you get x is 5 halves. So we let x be 5 halves. So left-hand side of the equation is a constant, so it's still 10. And then on the right-hand side, the first term is going to be 0 because we've got a factor of 5 minus 2x. Second term is going to be 0. Third term is going to be c times 5 halves squared. So 10 is going to be 25c over 4. And so this gives me 40 over 25 for c. And of course, I want to simplify that a little bit. So those are both divisible by 5. I can write this as 8/5. So c is 8/5. So now, since I don't have any other factors that I can make 0 in this expression, what I'm going to do is just plug in any old x value that's simple to work with. And the simplest to work with is x equals 1. And then I can plug in the values I already solved for. I've only got one missing constant here, so that's going to be the easiest way. Again, this approach won't work on the algebra for all of these problems, but it works on this one. So here, I'll let x be 1. I get 10 equals a times 1 times 5 minus 2, so that's times 3, plus b times 5 minus 2, so that's going to be 3, plus c times 1. And I already know the values for b and c, so I get 10 is a times 3, plus 2 times 3, plus 8/5. So I subtract the 6, 2 times 3 is 6, I subtract that, I get 4, and I subtract the 8/5, 4 minus 8/5 is a times 3. 4 is 20/5 minus 8/5, that's 12/5 is a times 3. And so a is 12 over 15. And that can be simplified to 4/5. So a decent amount of algebra in these problems, that's pretty unavoidable. But now we can write out our partial fraction decomposition and rewrite our integral with it. So the integral becomes a over, so for a, that was over x. So 4/5 over x plus b, that was 2 over x squared, plus c, that's 8/5 over, and let's see, what was our other linear factor again? 5 minus 2x. 5 minus 2x. And again, these are all pretty standard integrals. I'll rewrite them slightly. So we'll split this up, make it 4/5 the integral of 1 over x dx, plus 2 times the integral, and instead of writing as 1 over x squared, I'll write it as x to the negative second dx, plus 8/5 times the integral of 1 over 5 minus 2x dx. And of course, here, you need to do a u substitution. But again, that's a pretty simple u substitution that I'm going to skip. So this becomes 4/5 times ln of the absolute value of x for my first integral, plus 2 times x to the negative first power over negative 1 for the second, plus 8/5 times ln of the absolute value of 5 minus 2x divided by 2, plus a constant. And I'll just clean this up slightly more. 2 divided by negative 1 is negative 2. Instead of x to the negative first power, I'll write that as 2 over x. Plus 8 over 5 times 2, that's 8/10. But 8/10 is 4/5. Plus c. Now, normally I wouldn't bother with what I'm about to do, but oftentimes in online homework systems or textbook solutions, you will see answers written a certain way that is a little bit confusing for students. And since this is a good example for it, I'm going to go ahead and rewrite this a little bit further. I want to be clear. This is a final answer, and I'm totally happy with it, and you can totally stop there. But I notice I have this 4/5 times ln of x and 4/5 times ln of 5 minus 2x. So I can factor out the 4/5 from both of those and get ln the absolute value of x plus ln the absolute value of 5 minus 2x. Minus the 2 over x plus c. And now I can use one of my log properties. Log of a plus log of b is log of a times b. So you'll see a lot of times in textbook solutions or online homework, you will see them rewrite this using that log property. So this becomes ln of the absolute value of x times the absolute value of 5 minus 2x. Minus 2 over x plus c. And the last thing I'll do here, when we have the absolute value of two numbers, we can multiply those together inside the absolute value. So I distribute that x and I get 5x minus 2x squared minus 2 over x plus c. Again, totally fine with this answer, but because I know you're going to see this kind of solution pop up for these types of problems, just wanted you to be aware that that can happen. Okay, well that's it for that one. So we've done two cases so far. We dealt with a case where we had linear factors that weren't repeated. So we had two distinct linear factors. And then we had one of our linear factors repeating twice, the y equals x line repeating twice. So now we have to talk about irreducible quadratics. So here we're talking about our denominator contains irreducible. So irreducible quadratics essentially means unfactorable. Unfactorable. So we call those irreducible. And if you look here, this is the big difference. This quadratic expression we had here, x squared, can be factored into x times x. So what we're talking about in this section is things that cannot be factored. Things like sums of squares. So x squared plus 4 cannot be factored. One of the ways we know something can't be factored is that the equation, if you take the expression and set it equal to 0, it has no solution. X squared can't be equal to negative 4, so there's no solution to this equation, which is why we know that sums of squares can't be factored, because if they could be, that would give us the solutions to the equation. So in general, when we look at our quadratic formula, you'll often check, so negative b plus or minus square root of b squared minus 4ac over 2a. You'll often check the determinant, which is the b squared minus 4ac. If you have a quadratic that has 3 terms, and the b squared minus 4ac part of this formula is negative, that tells you that that thing has the equation would have no solution, and hence that quadratic wouldn't be factorable. Okay, so with that out of the way, let's go ahead and take a look. If we have a irreducible quadratic factor that is not repeated, then the decomposition will have a term of the form ax plus b over little ax squared plus bx plus c, little b plus little c, where cap a and b are constants. So in essence, we're saying is if we have an irreducible quadratic in the numerator, we should get a linear expression in the let me try that again. If we have an irreducible quadratic in the denominator, then we should have an irreducible, we should have a linear expression in the numerator. I'm getting myself all tongue-tied up here. Let's pause for 1 second. All right, we're going to see if I can talk again. So the decomposition will have a term of the form ax plus b over little ax squared plus little bx plus c. And if necessary, terms like this can be integrated by completing the square and using the formula, the integral of dx over x squared plus a squared equals 1 over a tangent inverse of x over a plus c. But that won't always occur. Just something you should keep in the back of your head. You may need to try completing the square to do one of these integrals. Okay, now let's take a look at the integral at hand here. We have the integral of x to the 4th plus 1 over x to the 5th plus 4x cubed dx. So first thing, of course, I'm going to do is factor this. X to the 4th plus 1 over x cubed times x squared plus 4 dx. And so when I look at this expression, x to the 4th plus 1 over x cubed times x squared plus 4, I have to think that this x cubed is really the linear expression x repeated 3 times. So I get a over x plus b over x squared plus c over x cubed. That's the expanded terms corresponding to my x cubed. And then for the x squared plus 4 in the denominator, I need a linear expression up top. And since we already used a, b, and c, we'll write dx plus e, a linear expression divided by this quadratic. Okay, so now I do the same general approaches initially to solving this algebraically. I get x to the 4th plus 1 equals a times, okay, what's my largest power of x? X cubed. So I'm going to have to multiply the a by an x squared since its denominator is only x so far. And then I'm also missing this x squared plus 4 factor plus b times. And again, we look, what's our largest factor of x? X cubed. So to get a common denominator, I'd need to multiply by x over x. So multiply by x. And I also need the factor x squared plus 4 plus c. Well, c already is divided by the highest power of x. So I'm only missing the x squared plus 4 part. And the dx plus e is divided by the quadratic, so I'm just missing the x cubed factor. Now again, I'm finding a common denominator here, so this is all over x cubed times x squared plus 4 on both sides, but then I cancel my denominators, and I'm just skipping that part of the process. Okay, so now we want to solve this algebraically. Because of these irreducible quadratics, it makes it a lot trickier because there's no real number. I could plug in imaginary numbers, but it becomes pretty complicated and doesn't always help make things easier. So I could plug in an imaginary number. I'm not going to do that. There's no real number that I can plug in to this expression. That's supposed to be x squared. Why did I write to the fourth? X squared plus 4. There's no real value number I can plug in to make x squared plus 4 0. And so that path isn't going to help a whole lot. If I plug in x equals 0, it might help me solve one of my constants, but it won't help me solve anything else. So I'm going to take a different algebraic approach this time. What I'm going to do this time is rewrite my equation, but I'm going to start multiplying out all my terms. So ax squared times x squared plus 4. So I multiply that x squared, I get x to the fourth plus 4x squared plus b times x multiplied here. So again, I'm just distributing. I get x cubed plus 4x. And I don't have to do anything to that x squared plus 4 here, but I'll go ahead and distribute the c to both terms in this step. So I get cx squared plus 4c. Plus, and same thing here, I got to distribute this x cubed. So we get dx to the fourth plus ex cubed. Okay, let's take one extra step of rewriting before we start combining things. Now I'll distribute this a, I get ax to the fourth plus 4ax squared, right? Just distributed that. Plus bx cubed plus 4bx plus cx squared plus 4c plus dx to the fourth plus ex cubed. So it didn't really have anything else to do on those last terms. Now what we're going to do is align all of our powers together. What do I mean? I mean, I'm going to look for all my fourth powered terms. We got a times x to the fourth. And over here we got d x to the fourth. And I'm going to factor the x to the fourth out of those. And that gives me a plus d times x to the fourth. I'm not doing anything to the left side of the equation again. Plus, now I'm going to look for all my third power terms. So that's bx cubed and ex cubed. And I'm going to do the same basic thing. I factor out the x cubed, I get b plus e x cubed. And here we've got 4ax squared and cx squared. So that gives us 4a plus c times x squared. Now there's only one term with x, that's the 4bx. And one term with the c, one constant term, just 4c. Okay, so now we can start solving by making a system of equations. So I'm going to rewrite my left side actually a little bit. And think of this as 1x to the fourth plus 0x cubed plus 0x squared plus 0x plus 1. And the reason I did that is to illustrate that if these two polynomials are equal to each other for all x, they have to have the same coefficients, which means a plus d has to be equal to 1. And b plus e has to be equal to 0. And 4a plus c also has to be equal to 0. And 4b has to also be equal to 0. And lastly, 4c has to be equal to my constant, which is 1. And now we have a system of equations. We have 5 equations. We have 5 unknowns. So now we go through and solve them. So c is 1/4. That one's nice and easy. B is 0. Also nice and easy. All right. Well, if 4a plus c is 0, then 4a plus 1/4 is 0. So 4a is negative 1/4. So a is negative 1/16. That's not too bad. B is 0, so 0 plus e is 0, which is nice because that means e is 0. And a plus d is 1, so negative 1/16 plus d is 1. Add 1/16 across, I get d is 17/16. Okay, well that's it. We've solved for all of our constants. Now we get to rewrite this integral. Remember, we always want to make sure we've got the correct factors paired up: a over x, b over x squared, c over x cubed, so forth and so on. So my integral is going to become the integral of a, negative 1/16 over x dx, plus the integral of b. Well, that's just 0. So I can go ahead and get rid of that one. Plus the integral of c, that's 1/4. And c should be over x cubed dx, plus the integral of, now we've got our quadratic expression, and that's dx plus e. So 17/16x plus 0 over x squared plus 4. All right, now we've got a little bit more work to do here. So this is negative 1/16 times the integral of 1 over x dx, plus 1/4 the integral of x to the negative 3rd power dx, plus 17/16 times the integral of x over x squared plus 4 dx. So over here on this last integral, we've got a nice little u substitution we can do. So that's what we're going to do. U equals x squared plus 4. So du is 2x dx. And I've got x dx in my expression. So I'll solve this for du over 2 equals x dx. And we'll just do several pieces of work at the same time. This is negative 1/16 times the natural log of the absolute value of x plus 1/4 times x to the negative 2nd power divided by negative 2 plus 17/16 times the integral of du over 2 times, and x squared plus 4 is my u, so put that there. That's negative 1/16 times ln of the absolute value of x plus, or I should say minus, because we've got a negative 2 in the denominator. 1/4 times 1 over negative 2, negative 1/8 times 1 over x squared, plus, we've got 17/16 times 2, that's 17/32 times ln of the absolute value of u plus a constant. And finally, meant to plug my u back in. That should be x squared plus 4. And actually, because x squared plus 4 is strictly positive, We don't need the absolute value bar anymore. Not on that one. Okay, that's it for that one. Now I've got one more case to talk about, which is where Q of x contains a repeated, irreducible quadratic factor. Okay, wow. Repeated, irreducible quadratic factors. So anything like this. We've got x squared plus 1. That can't be factored. It's a sum of squares. And it's repeated to the second power. So we'll start out by working on our fraction, our partial fraction decomposition. And since x is a linear factor, we'll get an a over x term plus. Now we've got our x squared plus 1 to the first power, and up top we should get a linear expression, bx plus c, plus. And now we get x squared plus 1 squared in the denominator, so that's going to be dx plus e. And we do the same old, same old. So we're going to find a common denominator. And then we're going to cancel that denominator. And so this term a is missing the two factors of x squared plus 1. So x squared plus 1 squared plus the bx plus c. For this expression, the denominator is missing the x. And it's also missing the second factor of x squared plus 1. And the dx plus e here, that's just missing the x factor. And again, we found a common denominator, we combined them, we canceled the denominators on both sides of the equation, and we end up here. And now I'm going to take the same approach I did to the last problem. I'm going to distribute x squared plus 1 squared, gives me x to the fourth plus 2x squared plus 1 plus bx plus c, and I'll distribute this x here. So I get times x cubed plus x plus, and now I'll distribute this x, dx squared plus ex. All right, do a little bit more algebra. Okay, we've got a lot of distribution to do here. Got x cubed times bx, that's bx to the fourth. X times bx, that's bx squared. We've got c times x cubed and c times x. And just rewriting those last couple of terms. And now we're going to group all our terms together again. So first I'll look for my fourth power terms. We've just got a plus b times x to the fourth. Now we'll look for any cubed terms. That's cx cubed. Well, that's the only one. So plus cx cubed. Some square terms. We got 2a squared, 2ax squared, bx squared, and dx squared. So that's plus 2a plus b plus d times x squared. And we've got two linear expressions left, cx and ex. So that's c plus e times x. And finally, a single constant, a. And now we can make our system of equations. A plus b has to be equal to 7. C, well, there is no x cubed term, so this coefficient has to be 0. So c has to be 0. That's a nice one. And then 2a plus b plus d. has to be equal to the 19 term. So 19 is 2a plus b plus d. Now there is no x term in the left-hand side, so c plus e has to be 0. And a is the only constant, and the only constant here is 7, so a is 7. So now we'll just look across and see what's easiest to solve here. So c is 0, so c plus e is 0 plus e equals 0, so e equals 0. So that's another nice one. A is 7, so I can plug that in over here. I get 7 equals 7 plus b, so b is 0. They don't all work out this nicely, but it does save a little bit of time. So now we've got b is 0, a is 7, and all we're missing is d. So 19 equals 2 times 0. Or sorry, a is 7. Let's try that again. 2 times 7 plus 0 plus d. So that's 19 equals 14 plus d. So d is 5. Okay, almost done here. Now we've got to rewrite our integral in terms of this partial fraction decomposition. And so a goes above x. So our integral is going to be the integral of 7 over x dx. And then plus, well, b and c are both 0. I'm going to write it all out. 0x plus 0 over... what's my quadratic expression again here? X squared plus 1. Of course, this whole thing is just 0. And then plus the integral of, and now we've got d, 5x plus e, which is 0, over x squared plus 1 squared dx. And so now we'll just integrate normally. This becomes 7 times the integral of 1 over x dx. I'm going to go a little quickly here. Plus 5 times the integral of x over x squared plus 1 squared dx. And for this one, I need to do a u substitution. So I'll write that over here. U equals x squared plus 1. Du is 2x dx. I have an x dx expression in the integral. So I'm going to make this du over 2 equals x dx. This becomes 7 times the natural log of the absolute value of x plus 5 times the integral of du over 2 times x squared plus 1 squared, which is u squared. That's 7 ln of the absolute value of x plus 5 halves times the integral of u to the negative second du. That's 7 times the natural log of the absolute value of x plus 5 halves times u to the negative first power divided by negative 1 plus c. And one more step of rewriting. 7 times the natural log of the absolute value of x. Got a negative multiplied in the bottom here, so this becomes negative 5 halves. And instead of u to the negative first, it'll be 1 over u, but u is x squared plus 1. And don't forget the plus c. Okay. Well, that's it for partial fraction decomposition. Thank you for watching.